Welcome back to ECE 320A. I think winter has arrived right after spring break, but you now can stay inside and finish up homework number 4, and if you work quick enough, you can start homework number 5. Exam number 2 is actually a week from Thursday, and there will be a review session a week from today after the normal class meeting on Tuesday. And if you haven't yet found it, there is practice material for exam number 2 on D2L. There's a unit in D2L exclusively covering exam number 2. Today what we want to do is pick up where we left off before the break, and we're going to go ahead and review or try to wrap up the low-pass filter example that we started. And this is done in the S domain, but it's done indirectly in the S domain, meaning we'll find the equations that govern the system dynamics in the time domain, and then we will Laplace transform those differential equations. After the exam, we'll actually start looking at being able to immediately rewrite the circuit in the S domain and do the analysis directly in the S domain. But again, we're sort of doing it in the S domain, but we're starting the process in the time domain. And we'll wrap that up. Then we'll talk a little bit more directly about inverse Laplace transforms via partial fraction expansion. And when can you perform a partial fraction expansion? When the degree of the numerator is strictly less than the degree of the denominator. And if it's not, then you need to perform some long division to get that remainder where you want it. And there's really 2 cases when you're performing partial fraction expansion. One is when the roots in your denominator polynomial are distinct, which means you don't have any roots on top of each other. And then the other case is when you do have repeated roots. And we'll look at both of those cases. We'll obviously start with case number 1. And then we'll show many different ways of finding these constants in the numerator expansions of your partial fraction expansion. And if it's set up properly, you could call those residues, but we'll probably just call them the partial fraction expansion coefficients, because we may put these numerator terms over something other than just a pure root. We might put it over a complex pole pair, but written in terms of real coefficients. And that will become clear, I hope, as we move through that discussion. Here's the problem that we started with last time. It's a low-pass filter. If somebody says design a low-pass filter, you can say, oh, is it passive? And if they say yes, then you can immediately write down a resistor and a capacitor, and you now have a low-pass filter. The bandwidth of that low-pass filter will obviously depend on the specific values of R and C. And R and C influence the time constant, and we'll get there as we go through this solution. But today's strategy, as I said before, is we're going to write the dynamic equations, or the equations that govern the dynamics of this system, in the time domain, and then once we have that differential equation, we will Laplace transform that differential equation, and that's where we will work the problem in the S domain. If we're thinking about a differential equation, just looking at that circuit, what can you anticipate ending up with in your differential equation? By that I mean, what's the order? It's first order because you have one energy storage device. And by inspection, then you can quickly start knowing some of the answer before you even have to start the solution. If we write a KVL in terms of what we've labeled on this diagram, that's pretty easy. We just walk our way around that single mesh. It's a series circuit, and we have Then we're going into the negative terminal of the voltage source. We'll say then minus V of t plus V sub r plus V sub c. We're back where we started. That needs to equal 0. But if we want to write these in terms of the capacitor voltage, we probably need to get rid of, well, we do need to get rid of V sub r. V of t is a given. That's our input. So that we can live with. That's whatever somebody says your independent voltage source looks like. And that could be a constant. It could be a sinusoid. It could be an exponentially damped sinusoid. It could be anything that they want to provide for you in V of t. Right now we'll just keep it as an unknown, but it's an independent variable. So we have to keep that in our expression. We now need to get rid of V sub r. And that's not that difficult because what's the current through that resistor relative to the current through the capacitor? It's the same, isn't it? I sub r is the same as I sub c because it's a series circuit. And we know, maybe even we have some outside. Did anybody see hail? I heard that when I was coming over. They said, oh, it was hailing earlier. That's not what I was working toward, but I was working toward ice, wasn't I? We know ice will give us the dynamic relationship, the current voltage relationship of this capacitor, and that now allows us to replace this current through the resistor, which is the same as the current through the capacitor, with C dV sub C dt. And all of that, you wouldn't even have to write all of this out, but I'm trying to be as direct as possible. Now we can substitute that right-hand side, RC V sub C prime, and replace V sub R of t in our original KVL equation to obtain the first order differential equation. And this is where I think we made it to last time before the break. We now have minus V of t, that's the given voltage source, and all the other terms involve the capacitor voltage and or its derivatives. And we just have one derivative, which is what we anticipated. This is a first order differential equation. You could rewrite that by dividing everything by this constant, r times c, and rearranging, take that V of t term and put it on the right-hand side of the equality sign. It now has a 1 over RC in front of it. The V sub c has a 1 over RC in front of it. And now we have normalized the coefficient in terms in front of our highest power derivative, or we now, well, we may not have much lecture left if my voice doesn't hold out, but I don't know what happened there. Maybe it was all the hail. It wasn't the ice, was it? So we've made this monic. In our polynomial in the denominator, our denominator polynomial will be monic, M-O-N-I-C, which just means that we've made that leading coefficient 1. And sometimes it's easier or cleaner to keep track of things when you've normalized that highest power to have a coefficient of 1. And factoring that out is what I've done essentially by dividing everything by RC. There's our differential equation. What we want to do now is solve that via Laplace transforms, and we can go into the frequency domain by Laplace transforming that equation. And Laplace transforming that equation really just means I can Laplace transform each term, since the Laplace transform is a linear operation. Now we're at a new location in the material, and so let's now work through that. We can Laplace transform the first derivative of the capacitor's voltage. We can Laplace transform, and let me go ahead, since the Laplace transform operation is linear, let me go ahead and pull out the scaling factor, 1 over RC, outside of the Laplace. And do the same thing with the forcing function. Now let's Laplace transform. And this isn't that difficult. The right two terms are straightforward. It's just the Laplace transform of v sub c and the Laplace transform of v. That just means we hit the shift key, we capitalize those, and replace the argument with an s. The only hard part is remembering that the Laplace transform of a derivative can be a little bit more involved. And what does that break down to? Differentiation in the time domain corresponds to multiplication by s in the frequency domain. Is there anything else? We have to take into account the initial condition, which sometimes is 0, but now let's go ahead and include that. This is now taking away the value of the capacitor's voltage at time t equals 0 minus. And we can now say, okay, that's plus 1 over RC v sub capital V sub c of s is equal to 1 over RC capital V of s. What I want to do now is, really I'm trying to find little v sub c of t, the time domain solution of my capacitor voltage. If that's the objective, what I want to do now is isolate these terms that are associated with the Laplace transform of little v sub c of t, which is capital V sub c of s. Let's now combine then the terms associated with that Laplace transformed quantity. Or I now have s v sub c of s plus 1 over RC v sub c of s. I can keep this term where it was, but now I've actually added the initial condition to both sides. And now it appears on the right-hand side of the equality sign. Let me factor out the Laplace transform of the capacitor's voltage to clean it up a little bit, the equation. And this is an important expression or an important polynomial. It's the coefficients that are scaling that Laplace transformed quantity that we want to solve for, and this we actually call the characteristic polynomial. Because once we start solving for capital V sub c of s, we're going to be dividing through every other term by that characteristic polynomial. And that now leaves us with capital V sub c of s is now equal to 1 over RC divided by s plus 1 over RC times V of s plus V sub c of 0 minus over s plus 1 over RC. And it's naturally separated into two pieces, the total solution for this capacitor's voltage. We have the first piece, which you could say is being driven or forced by the applied source. This I can call then the forced term in my solution. And the second term involves, now I only have one initial condition, but in general you could have a linear combination of a lot of different initial conditions if you had multiple energy storage devices. This is now the initial condition term. And until somebody gives us the initial condition and the structure of our voltage source, or what it looks like, is it an exponentially decaying waveform, is it a constant, is it a sinusoid, is it an exponentially damped sinusoid, before we're given that information, this is about as far as we can go. Let's now look at a couple of different scenarios. Suppose that somebody says, well, let's go ahead and assume that the capacitor initially had 2 volts across it at time 0 minus. And let's go ahead and assume that the voltage source that we're applying to that circuit, which again is a low-pass filter, is the unit step. We're just hitting the system with a 1 at time 0 and keeping that constant 1 value applied after we've actually started the initial condition on the capacitor at 2 volts. So now we need to fill in the right-hand side with the details that we've just specified in this first situation, which says, oh, if somebody's telling us our supply voltage is now a unit step, we now need to find its Laplace transform in order to plug it in where it needs to be in that expression. And what is the Laplace transform of a unit step? That's just 1 over s. And if this was a 7, if that was a 7, then this would be a 7. I'm not going to put that 7 in there. Now I have to be careful with my eraser. I'm just assuming it's a 1. Now we can put this 1 over s into that location for capital V of s, since we're told that's what it is in this first scenario. Or V sub c of s is 1 over RC, s plus 1 over RC, but we've actually now multiplied that by 1 over s, so in fact we have another s in the denominator. And with a voltage initial condition on the capacitor of 2, we can replace that variable initial condition from before and replace it with 2, and underneath that is 1 over RC. Now we can actually go ahead and get closer to what the capacitor voltage looks like as a function of time in terms of these parameters, which are the resistor and the capacitor in our circuit. To do that, let's go ahead and do a partial fraction expansion. And in fact, we've already expanded this a little bit just because of the way it was set up. That right-hand term we don't have to do anything with. We can immediately take that into the time domain based on what we know from our Laplace transform tables, what that looks like in the time domain. What we have to partial fraction expand is that first term, which is now a second order term or a denominator that has an s squared in it. And how would we do the partial fraction expansion on that first term? that okay? That last term was already in an expression that's consistent with some row in our Laplace transform table, some s plus a in the denominator, where the a is 1 over RC. If I ask on an exam, what's the structure of this capacitor voltage, you're essentially done. You don't have to find A and B. You just have to put this expression into a time domain form. If I say, what's the structure, then you would say, oh, he wants the time domain version of the capacitor voltage written in terms of yet to be determined coefficients, A and B. What happens when we inverse Laplace transform the first term? Negative ST. What? Is that what it is? Iced. If you say it, I better quit doing that. Okay, so this is just, what, a constant starting at time 0. That's the inverse Laplace transform of A over S is just A times the unit step. A weighting of A times the unit step. What about the B term? And the 2 is already there. And we're working all of these with t greater than or equal to 0. We're starting all of this, we're assuming everything is from t equals 0. We're doing the one-sided Laplace transform. And if you wanted to, and you can do this tonight at home, you should be able to find that A ends up being 1 and B ends up being minus 1. Yes? Is there a reason why the A term only has the unit step? So in this, that was the question. In this particular case, since I have included this term, I could actually erase that u of t. And so I want you to get comfortable with seeing this many different ways. I could have done that, but then I would have needed to put the u of t on the others. Another way of writing this could have been A plus B e to the minus t over RC plus 2 e to the minus t over RC u of t. Where u of t, now I'm using that as a switch. It's turning on all three of those terms at time 0 and leaving them on for all time t greater than 0. This is equivalent, the last expression that I've written is equivalent to the one just above it. Was there a question? Yes, so the question was, aren't you writing too much on the board? Is there some redundancy? And yes, there is in that first equation that I wrote down with the A u of t, but I wanted to emphasize when I was writing it down that that was coming from basically in the transform domain A over S. But once I've now said on the very far right t greater than or equal to 0, I could have erased this u of t. And then the redundancy is gone, but having redundancy is okay. But it's, I think students are getting confused as to why is there a u of t on all of these terms? And that's really just saying what the first equation is saying. This expression as a function of time is only valid for t greater than or equal to 0. I'm going to leave it in there. Okay, so I'm redundant. I'm probably going to say more than that that will be redundant today, but that's okay. Yes? So both answers would be acceptable on the exam. but this wouldn't be. Do you see the difference? So you need to say, oh, this is for t greater than or equal to 0. If we now plug in these coefficients for a and b, we can actually put some numbers to this, and we see that we have 1 minus e to the minus t over rc plus 2e to the minus t over rc. Okay, now I'll get rid of the redundancy. For t greater than or equal to 0. Those last two terms can actually be combined. They're the same in terms of their exponential structure. We have minus plus 2 of e to the minus t over. So really we have v sub c of t equaling 1 plus e to the minus t over rc, and I think you know where I'm going, times u of t. So I'm playing with this just to make sure you're comfortable with that option, or those options. They're equivalent. Pardon? Is what right? So I don't know. Yesterday I said the sine of pi was -1, so I'm questioning everything right now. So the cosine of pi is -1. I guess I was so excited about Pi Day, which is in a couple of days. It's on Thursday. Anyway, this is 2 minus 1 is what I was doing. Is that correct? So I have 1 plus e to the minus t over rc. And we could also write that as 1 plus e to the minus t over rc, t greater than or equal to 0. And what's that going to look like? Can you see that? Can you see what that is? At time 0, what should that be? If you evaluated this at time 0, what did we say the initial condition on the capacitor voltage was? 2, we said. And is it 2 from this formula? And it's just going to, eventually, where are we going to end up? For high t, for a large value of time, where are we going to end up? 1. There's 1. Now it's really going to be critical for me to try to sketch this, but this is now, something like that. Okay? And if we anyway, you get the idea. Let's say those are time constants. This is now, what is our time constant tau? We really are looking for e to the minus t over rc minus 1, are we not? That's sort of what we're doing to try to find the time constant. We want to know, when is that expression in the exponent going to equal 1? Well, at what time? So here, what I should say is when this is at t equal to tau. At t equal to tau, where tau is our time constant, that now says that we will have t over rc evaluated when the time is set equal to tau. When that's equal to 1, we solve that for tau. And now you see that the time constant is this RC product, which you've probably heard, or, it's the RC time constant. In a first order resistive capacitive circuit. So if this is one time constant, where are we now in that numerical value? Can you say where we're at? Isn't it there? 1 plus e to the minus 1, and e to the minus 1, 1 over e. And e is roughly 2.7, isn't it? So now you're 1 over 3 roughly in broad terms. So now you're 1 plus. So that's not drawn maybe as accurately as it should be. But after 5 of those, where should you be? So after 5 time constants, that's what we say is our 1% settling time. And that's going to be very close to 1, within 1% of 1. Okay, there's one example for that RC circuit. Suppose we looked at a second. Suppose that we now say, let's not have an initial condition on our capacitor voltage. And let's apply a waveform that's actually a sinusoid. Let's say that it's A cosine omega t, u of t. Now I'm using that u of t as what? A switch still. I could say this is A cosine omega t, comma, t greater than or equal to 0. Same thing. Now when we Laplace transform this, what you don't want to do is look in the table and find the Laplace transform of cosine, look in the table for the unit step and multiply them together. No, 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 don't do that, okay? So that's when you might want to say, oh, just to remind me, maybe this needs to be written that way. And most of your tables are tabulated for right-sided or waveforms that are causal, or waveforms that start at 0 and continue for non-negative values of time. What's the Laplace transform of a cosine? Omega over S is what I heard. That's a unit step of amplitude omega, isn't it? That's not a cosine. Is it a sine? S-I-G-N or S? Is it a stop sign? It should be a stop sign if that's what you're doing. That shouldn't be there, should it? In a cosine. So this needs to be A S squared plus omega squared. That's the Laplace transform of a cosine. Now we can plug that in to our expression, Laplace transform expression for the capacitor voltage, which initially was 1 over RC S plus 1 over RC times V of S. And V of S now we have. That's now this AS over S squared plus omega squared. Now we have a cubic in the denominator. Let's look at this with a few more specifics. Suppose we go ahead and let our product of R and C be 1, something nice. Now we have 1 for the RC time constant. Suppose we let omega be 2. What are the units on omega? That's our frequency of oscillation on that cosine. We're saying it's now 2 radians per second. And let's go ahead and assign an amplitude to that cosine. Let's say the cosine is an amplitude of 3. We're now applying to this low-pass filter a cosine of amplitude 3. We're going between 3 and minus 3 with a frequency of 2 radians per second. And the filter now we've designed. We've said the RC time constant is 1. 1 second, actually. It's in units of time. Plugging those numbers in, we have 1 over s plus 1 times 3s over s squared plus 2 squared. Can we partial fraction expand that? And what am I asking when I ask that question? Can we partial fraction expand? And the answer is yes. I flipped a coin and got yes. So what I was asking really is it strictly proper, that transform expression? And it is. The denominator polynomial is bigger than the numerator. And what's my partial fraction expansion look like now, structurally? Or what are you going to see in your answer? What would you expect to see? You now have a low-pass filter, and you've applied a cosine waveform to it. What do you expect to see as the capacitor's voltage? And a long time from now, what do you expect to see? Do you expect to see anything? Is everything going to decay? It's a low-pass filter. It's oscillating but decaying. Is this confusing? So think about what we've got here. You're now shaking this circuit at 2 radians per second. And do you quit shaking it? What was V of t? It was a cosine, wasn't it? Did it ever stop? No, it had an amplitude of 3. Did you see that amplitude with 3? I apologize if you're listening to this at home. You're not getting all the graphical or the visual. You're seeing something shaking with amplitude 3 and a frequency of 2. And won't you see that same frequency throughout your circuit when you look at it? And when will you sort of say, well, after a long time? What's a long time now in this circuit? 5 seconds. So you just have to wait 5 seconds, and you're now at steady state. You're at sinusoidal steady state. And sinusoidal steady state says every signal in that circuit is going to be shaking at 2 radians per second after 5 seconds. So what's the partial fraction expansion look like? How many terms do I have? All right, I should be, I don't know what, selling things here. I hear a 1, I hear a 1, I hear a 2, I hear a 2. How about a 3? A 3. 3. How about a 4? 4 terms? Do I have 4 terms in my partial fraction expansion? How about a 5? Anybody want to do a 5? 5, okay. Now about 6. Sorry, I'm getting frustrated with this counting exercise. Where should I stop? Are you getting 3 because that's in my numerator? Will I have this term? Will I have that term? What is that term going to be in the time domain? A cosine. Am I done? You think so? So if I'm done, that means that the output waveform, the voltage across that capacitor, is just a pure cosine, which means that's exactly what I'm injecting in at the source. That means that if I looked at the peaks on that capacitor's voltage would be right in line with the applied voltage peak. No time delay, no lag in my circuit. That's not quite the case, is it? So I'm going to actually have a shift. If you looked at the oscilloscope display and said, okay, here's the trace of my voltage source, and here's the trace of the capacitor voltage, they're both oscillating at 2 radians per second, but one is shifted in time relative to the other. And that shift is not going to occur with just 2 terms. We need to have the sine term in there as well. And the sine term is C. Here's the omega, and omega we assign to be 2 s squared plus 2 squared. So 3 buys the product. 3 is the winning answer. And now we can find A, B, and C. We can, and don't go home and said, they say, what did you learn today? My ABCs? They're going to stop paying your tuition if you say that. Yes? So why do we need, that's why I tried to kind of emphasize this. Why do we need the sine and the cosine? If we didn't, well, I'm not going to be able to draw this. That's why I wasn't drawing it. But suppose this was the, when we're in sinusoidal steady state, suppose that's V of t. Now, if we didn't have that sine term there, that means that all we would have is the cosine. Maybe it has a different amplitude, but its peaks and valleys are aligned. Okay, use your imagination. This red is now V sub c of t without that c term, without the sine. But it's not going to be right aligned. You're going to have a phase shift. There's going to be a delay between the application in the sinusoidal steady state. There's going to be a delay between the applied voltage and the voltage across your capacitor. And to put that in to the final answer, we need to have a linear combination of a cosine and a sine of the same frequency. Now that could also be written equivalently as a cosine with a phase shift. And that's just a trig identity. The sum of 2 angles on a cosine, you can now push that through and see that, oh, I have a cosine plus a sine of the same frequency. So what I'm saying is because of that C term, or that third term, now we might have something to the, I'm drawing challenged, but we might have something like this. We have an offset between the peaks and the valleys in the sinusoidal steady state. And this is now V sub c of t. Think about that or reflect on that later, but now anytime somebody hits your system with a cosine, you're going to have a sine and a cosine pop out, just generically. If it happens that you're aligned, then C will be 0. You'll do the partial fraction expansion, you'll solve for C, and C is 0, and you go, that red line is aligned with the blue line. But by default, you need to introduce the sine and the cosine components to give you the possibility of a phase shift between the applied signal and what you're measuring. If I now shake this with a sine, you're going to get a sine and a cosine. If I do the shaking with exponential decay, you're still going to have a sine and a cosine with the same oscillation. Exponential decay will be the same. Can we find A, B, and C? I'm not sure that fully convinces you right now, but if we can now compute an A, B, and a C that are none of those are 0, then we know that that's what we have for our time domain expression based on this partial fraction expansion. How do we find A? Now we can do it the cover-up method. All of these poles are unique or distinct. Here I've actually written it in terms of real coefficients. You could solve this as a K1 over S plus J2 or S minus J2, and then a K1 star over S plus a K, where was I? An S minus J2. This was S minus J2, this was S plus J2. Let's just do it this way for now because these are in the table. Okay? What's A? If I multiply every term in this expansion, so the blue is on the far left and the black is on the right, I multiply everything by S plus 1, that factor, and evaluate it at the value of S that causes S plus 1 to vanish, and then the only thing that's going to be left on the right-hand side is A. Everything else is going to vanish when I plug in S equal to minus 1. On the left, I'm going to be canceling the S plus 1 factors that I've multiplied through by, and I end up with then A, this is the cover-up method, A is now equal to 3S over S squared plus 2 squared, which is 4, evaluated at minus 1. This is now 3 times minus 1 squared plus 4 minus 3/5. That's going to weight my decaying exponential. Now, what if here I'm going to do something different from the cover-up method because I really don't have this written in the standard distinct pole representation. That would have required me to write this as a plus K, K1 over S minus J2 and plus K star over S plus J2. I didn't do that. I kept real coefficients. Now I'm going to show you a strategy for finding B. And what I'm going to do, is it clear that that blue is over here? That's now on the left, and A, B, and C terms are on the right. What I'm going to do is I'm going to multiply all these terms by S. And then I'm going to let S go to infinity. Okay, new technique, new strategy. I'm trying to isolate and find an equation or equations to determine B. And I'm going to call this the limiting value of S. So here's what I'm going to do. I'm going to say this is the limiting value of S strategy. So I now am looking at the limit as S goes to infinity of the left-hand side, which had one S already in the numerator, but I'm multiplying by another one, so it's going to be 3S squared. And downstairs I had S plus 1, S squared plus 4. What's that equal? Well, let me write the other side. So now I have the limit as s goes to infinity of a s over s plus 1. I'm running out of space, but I have an infinitely wide piece of paper. You don't. Oh, that's not fair. Yes. Plus, can I go on now? Sort of. I'll hit a carriage return in a minute. Now we have b, s, but we put in another s, and this is s squared plus 4 plus 2c s over s squared plus 4. All I've done so far, I haven't taken the limit, I've simply multiplied both sides by s. That's all I've done. And this partial fraction expansion is true, it's valid for all values of s. Now let me take the limits. What's the limit on the left-hand side as s goes to 0? I'm sorry, as s goes to infinity? 0. I was giving it away, wasn't I? I have s squared over s cubed, or 1 over s, which when s goes to infinity, that left-hand side equals 0. In the first term on the right, what happens as s goes to infinity? I get a, don't I? What about the second term? I have s squared over s squared. Those are approaching infinity at the same rate, so I now have plus b. What about the third term? I have s over s squared, which is 1 over s. As s goes to infinity, that goes away. Now I have 0 is equal to a plus b. Another equation that allows me to find b if I have a, and I just found a. This now says, oh, b is now minus a, and a was minus 3/5, so b is 3/5. I'm kind of showing you all of these tricks before I formally go through them. So now we have a and b determined. If this blue and black equation is true for all values of s, let me just pick a convenient value of s and solve it. And what's a convenient value of s? Well, it's definitely not any of the values of s that cause the denominators to vanish. Then I would end up with infinity is equal to infinity. Doesn't tell me anything. Yes?
You use s equals 0 to find c. Sorry, did I go ahead?
That's fine. That's what I'm wanting. I want you to think ahead. So the comment in class was, can your convenient value of s be 0? And why would you maybe do that? Well, it's not going to make your denominator vanish, and it will make one of these numerators vanish. So that's a pretty convenient value. So a convenient value would say, oh, let me go ahead and let s equal 0, and now I can say 0 on the left. Do you see the blue? If I plug in 0 for s, that whole left-hand side vanishes. I have 0 over 1 times 4. 0 over 4, that's good. That's 0. Equaling what's on the right. I let s equal to 0 in the first term. I just end up with a for the first term. What about the second term? It goes away because I've set s equal to 0. And what about the third term? I have 2c over 4, or c over 2. So now I have another equation that involves c and some unknown and an already determined constant a. That being said, I have 0 is equal to a over 1 plus b 0 over 4 plus c 2 over 4. Or Wasn't a minus 3/5. We double it and negate the sign. Now c is 6/5. Or we now have v sub c of s is now minus 3/5 s plus 1 plus 3/5 s over s squared plus 2 squared plus 6/5 2 over s squared plus 2 squared. I now will argue that you can immediately find these expressions in a table and immediately write down the time domain expression for your capacitor voltage. The first term that's the first term. The second term, that's now the cosine, and it's oscillating at 2 radians per second. And the last term was our sine term. Everybody okay with that? All of that discussion was motivated by a low-pass filter. Do you see how you could draw out your interview with somebody and they go, tell me a little bit about a low-pass filter? How much do you want to know? And does that answer seem to make sense? Now, this component of your sinusoid is aligned with your source, but this one, the sine piece, is offset, and their combination gives you this phase shift if you just drew those two curves as one. And you'll draw those two curves as one after how much time has elapsed. When that exponential is basically gone, and that exponential will be gone after 5 time constants. And what's the time constant for this exponential? It's the value of t that causes that exponential to be minus 1. And that's when t is equal to 1. So 5 of those 1s, 5 seconds. After 5 seconds, all you really have left will be this cosine and sine term. And what I would suggest that you look into now, tonight, is, can I rewrite that cosine and sine at the same frequency as a cosine that's shifted in time, or as a sine that's shifted in time? And the answer is yes. All right. Let's now go into the formal discussion, like everything is formal in this class, as the inverse Laplace transform. Maybe next time we do need to have a formal class and everybody will come in tux it. All right, so here's the inverse Laplace transform. And the way that we're doing this is using tables. And so we're trying to now find transform pairs in these tables. And that's going to occur or appear via this partial fraction expansion. And the nice thing about this partial fraction expansion, which we've already used in the previous example, is that it's valid for all values of this complex frequency variable s. And let's now look at the first case, which is when we have distinct roots. So we're wanting to find little f of t, and suppose that now somebody gives you capital F of s equaling 2s squared plus s plus 4 all over s plus 1 times s plus 2 squared plus 3 squared. A lot of times I'll just refer to the numerator polynomial as n of s and the denominator polynomial as d of s. What's our first step in this inverse Laplace transform procedure or process? What's the first question we need to ask ourselves before we do anything else? Is it formal? It's as formal as f can be. This is an f, so this is f of s. Is f of s not formal, but is it strictly proper? Is it? If I say verify or validate your answer, how would you do that? If you just say yes, all I know is you've maybe had a lucky coin toss. So how would you convince the grader that yes is a valid answer? You would say, oh, my check is the degree of d of s is what? What's the degree of the denominator? 3. And that's strictly bigger than the degree of n of s, which is 2. So 3 is bigger than 2. Where are the poles located? Or, if you've forgotten what poles are, since they took our tents down on the mall, we've forgotten about poles holding up those tents or circus tents. But these are now the values of s that cause the denominator polynomial d of s to equal 0. Those are the poles. So now we look at those of d of s, and we have s plus 1, and then we have s plus 2 squared plus 3 squared, and you're going, why does he keep writing it in that form? Well, the first form, I factored it out, actually, and I factored it in a way that preserves real coefficients. Because, in fact, that bracketed term, or the square bracketed term, has complex conjugate roots. And I don't want to play with complex numbers, maybe. But in this case, I could now say, well, I have one pole when that first factor vanishes, or when s plus 1 is equal to 0. So there's s equal to minus 1. How many poles do I have? 3. And so here's the first one. Let me call it s sub 1. That's at minus 1. Now let's look at this second term. Set equal to 0. Well, if I do something similar to what I had before, let me move that constant term to the other side. I now have s plus 2 squared is equal to minus 3 squared. Well, I don't like that squaring. What if I take the square root? Square root of minus 1? That's just j in electrical engineering, isn't it? It's I a lot of other places. Plus or minus, because we took the square root. So now I can say I have s plus 2, taking the square root of both sides, is plus and minus j 3. We okay with that? I've just taken the square root of both sides to try to get something that I can now solve for s. I can subtract 2 from both sides and end up with my second set of pairs of poles. So that now adding or subtracting 2 from both sides, I see that s is minus 2 plus and minus j 3. Or s sub 1 is now, I'm sorry, I've already used up s sub 1. S sub 2 is minus 2 plus j 3. And s sub 3 is minus 2 minus j 3. And do you see now why I wrote that polynomial, that quadratic polynomial, in the form that I did? Now you can immediately see, oh, the real part is minus 2, and the imaginary component is the 3. And that's explicitly identified from that s plus 2 quantity squared plus 3 squared. Now looking at that, you go, oh, my roots are at minus 2 plus and minus j3. Boom. You're done. You don't have to do this again. Now, what's my partial fraction? So, are my roots distinct? Am I in case 1? Is S1 equal to any of the other roots? Is S2 equal to any of the other roots? No, they're conjugates. So one's up top, one's down below. They're not any of those poles lying on top of each other. And where are they located? Or what's my partial fraction expansion? I now can say that capital F of S is now equal to A1 over S plus 1 plus A sub 2 over S plus 2 minus J3 plus A sub 3 over S plus 2 plus J3. And now let's just convince ourselves where those 3 poles are in the complex S-plane. And I'll do this 3 different times. The first term gives me a pole at S equal to minus 1. I'm in the left half plane of the S-plane. Where's that second? And now I'm giving the answer away a little bit because I've emphasized the left side. So if you solved that denominator for S, you set S plus 2 minus J3 equal to 0, and where are you going to end up? What value of S will cause that to vanish? That's where I'm going to locate one of these poles. It's at minus 2, and what's my imaginary part, up or down? This is where you typically will get some confusion, but this factor actually corresponds to that pole in the second quadrant. That value of S is when it's minus 2 plus J3, and you put that in for S, and the denominator vanishes. There's your pole. What about the third term? It's also minus 2n, but it is actually downstairs at minus J3. That third pole is now down here. And its location then is at minus 2 minus J3. Make sure you're clear on that, or comfortable with that, because we're going to really eventually see that A2 and A3 are complex conjugates. And if that's the case, we really only need to solve for one of those. And we're going to isolate or focus on looking at the partial fraction expansion coefficient associated with the pole in the second quadrant, because that's what our formulas will be based on. What is A1? We can obtain it from the cover-up method. We can do all of these via the cover-up method because they are distinct. We multiply both sides by s plus 1 and evaluate at s equal to minus 1. Let me write it out completely. We now are multiplying f of s, the left-hand side, by s plus 1, and then evaluating it at s equal to minus 1. Or the numerator is the same. It's 2s squared plus s plus 4. But now we've canceled the denominator, one of the factors in the denominator, the s plus 1 factor, and we're left with s plus 2 minus j3, s plus 2 plus j3. Or you know that you could rewrite that as s plus 2 squared plus 3 squared. And I'll encourage you to go home and see that if you just multiply that out, that's exactly what you get. Because you can use FOIL, first term, and now treat it as if this is one of your terms. And then you have your second term. So you have s plus 2 squared. The cross terms cancel because you have a plus and minus j. And then the last term is going to be j3 squared with a minus sign, but j squared is minus 1. So you end up with plus 3 squared. We're trying to find a sub 1. So if we did it the brute force way and plugged in minus 1 for s, and if we kept it in the factored form with the complex roots, we could still do it. We could say, oh, this is minus 1 plus 2 minus j3 minus 1 plus 2 plus j3. Or if we used our real coefficients, we would really have maybe an easier time of it. We would have minus 1 plus 2 squared plus 3 squared. You'll get the same answer. But the bottom one in black is easier to do. You have 1 squared plus 3 squared. That ends up giving you 10 downstairs, and upstairs you have 2 minus 1, I think I did that before, 1 plus 4, or I should have 5. A1 is 1/2. What's a sub 2? We can do it the same way. To find a sub 2, what do we multiply f of s by? We multiply it by the factor that's sitting right underneath a sub 2. So that's this factor s plus 2 minus j3. We have s plus 2 minus j3 times f of s. And where do we evaluate that? S equal to the value of s that causes that factor to vanish, which is minus 2 plus j3. Do you see how you could get tripped up if you were not paying attention? But now, what does this equal? This is the same numerator, 2s squared plus s plus 4. We have the s plus 1 factor still there, and we've only canceled one of those complex factors. The other one is remaining, and that was s plus 2 plus j3. And we're evaluating this at s equal minus 2 plus j3. Where this and that, this is the value of s that causes s plus 2 minus j3 to vanish. Now you can plug in that complex number for s and solve for a sub 2. And I'll maybe do that after class since everybody's getting nervous. It is a little bit late. I'll let you go. Be safe, and we'll see you on Thursday.